Now we want to talk about force between multiple charges. We will compute this using principle of superposition. So we want to compute net force on a charge, and this charge is surrounded by a bunch of other charges. So net force on a charge is equal to vector sum of forces exerted on this charge by all other charges. So let us see this. We have a charge Q1 and it is being pulled or repelled by Q3, Q2 and Q4. So force acting on Q1 is the force exerted on 1 by 2, which is F12, then F13 vector, that is force exerted on 1 by Q3, and then F14 vector, which is force exerted on Q1 by Q4. Now very importantly, we are not worried about the force acting between say Q3 and Q4, Q3 and Q2 or Q4 and Q2. Now let us see an example where we use this principle of superposition. So say you have an equilateral triangle, you have three charges small q placed at its vertices, and there is charge capital Q which is at the center of the equilateral triangle. Now we assume that capital Q and small q have opposite charges. You could say they have same charges, but for this problem we are taking them as opposite charges. So I'm right now just marking the angles. So this is an equilateral triangle and that's why we have 60 degrees and 30 degrees as I have marked. So there are three forces acting on this capital charge Q. All three forces are pulling capital charge Q towards small charge Q. And as I mentioned before, we assume that this force is attractive, that is Q and small q have opposite charge. Now the problem would not change if you make it same charge, and that is because of the symmetry of this problem. So there is a force acting in this direction, we call it F2 vector. There is a force acting in this direction, we will call it say F3 vector, and there is a force acting in the upward direction which we call as F1 vector. So first we talk about the force. So the formula for force is K times capital Q over small q divided by A square, where A is some distance. Yeah, so we are talking about the magnitude of the force, so I am not talking about or not worried in the sign of capital Q or small q. Now since capital Q lies at the center of the equilateral triangle, all three forces acting on it are equal. So just by symmetry now you can say all these three forces acting on point Q are equal and they are equally spaced. That is, the angle between F1 and F3 is 120 degrees, angle between F1 and F2 is 120 degrees, and angle between F2 and F3 are 120 degrees. So the angle between all three forces is the same and their magnitude is the same. So by symmetry the net force acting would be 0. But let us now solve this and show it more concretely. You could have stopped the problem here, but we will fully solve it. So in the vertical direction you have F1 vector which is going up, and from this magnitude you subtract total force going down. So the total force going down is, first you see that you have the component force which I am marking in green as downward. So this is F2 cos of 60 degrees, and you similarly have F3 cos of 60 degrees. So F2 cos 60 and F3 cos 60 are both pointing downward, since both F2 and F3 make an angle of 60 degrees with the vertical axis, that is the y-axis. So here by absolute value we mean the magnitude of the force. So F2 cos 60 plus F3 cos 60. Now cos 60 is nothing but half, and all these three forces are equal to F. So this will come out to be 0. So vertical component is 0. Similarly, we will see the horizontal component is 0. For horizontal component, it's very easy to see. So force in this direction, this will be cancelling out the force in the right hand side direction of the x-axis. So on the one side you have F3 sine 60 minus F2 sine 60 as the net force acting in the positive x-axis. Now F2 and F3 have the same magnitude as F, and you do the calculation and you see you get 0.